Good morning. Thank you for the possibility to be here today at this wonderful event. My name is Heiner Guschall. I was introduced and I have the chance to present here the second part of our presentation before I turn the word to Andreas Melcher. So it was mentioned already by the colleague from Volkswagen how basically the steps of end-of-life vehicle recycling are working. We regard end-of-life vehicles as a source for industrial mining. We are focusing today just on the ferrous metals, but there is much more. We have the polymers, we have the non-ferrous metals, and when we see at the right diagram, we see that nearly over the last 20 years, the total content of metals was more or less on the same level, although it's always claimed that the rubbish or the waste content in end-of-life vehicles is increasing. Matter of fact, ferrous is slightly decreasing, non-ferrous metals are increasing. We are working with Volkswagen already more than 25 years, nearly 25 years, and also polymers have been injected in blast furnaces at Salzgitter and first Alpine, and it was initiated at that time always by Volkswagen. Just to mention it, of course, when we are talking today about scrap processing and the shredding process to achieve a crafted scrap from end-of-life vehicles, shredder process is in general designed for the liberation of complex material to produce from composites, from electronic scrap, from everything which contains a high share of non-ferrous metals, a defined end product. When we see the total process, we are focusing today on the upstream process, the shredder itself, and the downstream process. On the left side, the end-of-life vehicles, the dismantling, the depollution has already been mentioned. The upstream process, I don't look in detail on the baling and flattening. It could be a topic in the future when maybe cars are processed in centralized plants, when car manufacturers want to get access to the raw materials, then optimization of the transport route becomes an important topic. I'm focusing on upstream, which means pre-shredding, in our case the EcoRec Neo. I explain the benefits, especially when we integrate it into the recycling process of cars, the shredder process itself, and the most important, that's the downstream process. In our case, we call it scrap tuning to produce the defined and quality shred. The upstream process means pre-shredding. It's state of the art, and anyway, or nevertheless in Europe, not in many locations implemented. We do it in general in a way that we combine it with a screening step to remove dirt, which reduces the cost of the process, the overall shredding process significantly. You add less than €1 per ton for the cleaning, for the removal of stones and dirt and glass, but you reduce the wear cost in the shredder by €2 to €3 per ton. So this step makes, in any case, sense. Oh, sorry. The shredder, the pre-shredding step itself has significant advantages besides environmental impacts and environmental safety, avoidance of explosions. It has impact on the operational safety, detection of shreddables by sound detection. Densification in the main shredder is increased, and this again has important impact on the quality of the final scrap because density and impurities correlates with each other, and it has significant economic benefits. You can, by integrating a pre-shredder, you can fully automate a shredder. Basically, it can work without a dedicated operator. You reduce the power consumption and the overall, as already mentioned, wear cost. The shredder itself, it's traditional, and whoever's the manufacturer, the differences are not significant. You have a feed roll system, you have a bottom grade, you have a top grid, and the hammers, swinging hammers. The most important is the design of the grids. It has major influence on the density, the feeding system, and the control. This is very important. I will use later the word full box shredding. This is basically the goal we want to achieve. And this we achieve by automation, feed roll control, and the drive system. Everything then combined in the automation system. Basically, we can come to conclusion. The main differentiation of a shredding plant lies in their level of automation, drive concepts, and the downstream, not necessarily in the shredder box itself. Very important, today becoming more popular, but still not state-of-the-art, is the use of frequency-controlled drives in shredders, even up to 6,000 horsepower or more. It makes the operation and the automation of a shredding plant much smoother. You can reduce the energy, you can reduce the power peaks. This is, in times of unstable grids, also very important. And you can drive the shredder much more on the maximum torque on a constant level, so that you achieve the full box shredding. And with achieving the full box shredding, you maximize the density as well as the throughput of the shredder, and basically you come also to an economic optimum. Now the most important, the downstream process. In our case we call it scrap tuning. This might be in some cases slightly a little bit different, but basically these steps are essential. We have in the first step a long part separator, we call it poker separator. In some cases it can also be a screen. When steel manufacturers want to use shredded scrap in the blast furnace or for direct feeding a smelter or somewhere else, it is very important that the material is very homogeneous. So long pieces and oversized material is negative. So this step, either in here the poker separator or screen, makes sense to remove oversized material, and also to make sure, in case of an emergency of a shredding plant, that material is discharged, contaminated material, and is not going up to the end to the finished product. The next step is the ferrous separation. Such a max stand, double max stand, is state-of-the-art. In the meantime, sometimes even 3 magnets. In our case, the second magnet is so-called under. It's separated under the magnet and not running over the magnet. This increases the area and for cleaning significantly. And when the magnet is also controlled by VFD, you achieve a much better cleaning. Still, after the magnet separation, there can be some organic impurities. These are separated by another sifter. In the US, standard. After the magnet, in Europe, not very usual. But if there is some foam or something inside the scrap, this is removed, in this case by an air knife or air classification. Very important is then the last step, which is the crafted scrap module, which separates the metals or the scrap based on its chemistry, and this is shown 2 slides later. And the last step is the EcoScan, which analyzes the scrap. It's not sorting, it's just reporting. And by doing this, each load can be assigned with a certificate, so that the melt shop knows exactly the quality. The left slide shows such an air classification, that organic material, which might be in the material, is still removed. And the right slide shows clean scrap, which does not contain any free copper anymore. Should be the dream of any steel plant. The downstream process, scrap cleaning, the automized sorting. This is shown here. We call this unit EcoFlip. It's a combination by AI-based optical control plus XRF analyzing, so that each piece which is on the belt is analyzed based on its chemistry. so that we can define a final scrap quality, and the sorting algorithm is then sorting according to this to achieve this target. It can work up to 200 tons per hour, so it fits basically to any size of shredder. Very important is such a case that we have at the end the online analysis. That means that any heavy metals can be sorted, can be analyzed in a precision which comes very close to the melt shop analysis. And at the end we have a reporting system to the melt shop, so that the melt shop knows at any time which quality and which chemistry they get, so that they can optimize the use of shredded scrap based on the chemistry and not anymore based on historical data. These are just slides which can be customized. You see the tendency of the different elements. You get hourly reports per batch or daily reports. There can be a benchmark between different shredding plants, so that you can use the data also to make a better assessment of your procurement of scrap, that procurement costs can optimized and perfect case can be lowered. The target chemistry of such a crafted scrap is that you have a homogeneous size, roughly 100 millimeter. This can vary depending on the customer. You have a high density, 1.2 to 1.4. You have a ferrous content of over 97%, and a copper content which can be adjustable between 0.1 and 0.15. Also chromium and nickel content can be adjusted. It can also be the case that you give a maximum composition, and the sorting algorithm will then sort the scrap according to this. There is a certain variation of this process, especially when we look at the end-of-life vehicles. We have different kinds of steel, and the sorting can be done to achieve different qualities, so that we can come to a cradle-to-cradle recycling, that special steel plants get their quality back, so that we are not making everything just by diluting, so that we really can live circularity. And basically this is already the end. I hope I'm more or less in time, and would give the word to Andreas.
The second one, maybe this is for you, Heiner. What is the standard copper level after end of life of vehicle shredding as compared to the numbers presented?
Mm-hmm. So the standard for shredded scrap, according to the European scrap specification, is 0.25. Reality is, in many steel plants, that today, when using the majority of the shredder feedstock with end-of-life vehicles, that the copper level is in the range 0.3 to 0.4. So it is much higher, which is a consequence from the complexity of new cars. We have heard that there are more non-ferrous metals, and older plants don't have the separation efficiency of newer plants, which has led during the past years to a steadily increasing copper level in the shredded scrap.